Hi everyone, in case you don't know me, I'm Dr. Rosenthal, and today we're going to be learning about nuclear equations, how to balance them and how to write them. We're going to begin by reviewing briefly the types of radioactive particles, then we're going to look at an example of a nuclear equation, and then we're going to learn how to balance it and also how to use table N to write nuclear equations. So let's begin. Let's quickly review what we know from Table O. In this table, we have a list of the radioactive particles. We have alpha particles, beta particles, neutrons, protons, and positrons. And we have the symbols for these radioactive particles in the right-handmost column. So we're going to be referring back to this table as we write nuclear reactions. So keep in mind that you have this tool in your toolbox to use when you need it. Let's take a moment and look at this example of a nuclear equation. We have a uranium-238 atom on the left, it's the reactant, and it's decaying into two products, thorium-234 and a helium-4. Now right away you should recognize this particle is familiar to you because this, according to Table O, you can refer there for a second to remind yourself, is an alpha particle. So when we have an alpha particle being produced in a nuclear equation, we can classify this reaction type as alpha decay. Symbolized, and the alpha particle has the following symbol. So this is alpha decay. Another term for this type of reaction, we can classify this reaction as a transmutation reaction. Here we have a uranium nucleus being converted into a thorium nucleus. So we've changed the identity of the element. And whenever this happens in a reaction, we call it a transmutation reaction. And that happens because the nucleus is either gaining or losing protons or neutrons. So you should be familiar with this term so you can identify for a given reaction if transmutation is taking place or not. Let's look at the reaction now to try to determine how or why this is a balanced nuclear equation. What makes it balanced? So in order for a reaction to be balanced, it has to be balanced for both charge and mass. Now the number down here, which we also refer to as the atomic number, we're going to call the charge. So this is the charge of a uranium atom. It's 92. So the idea of a balance is that the number on the left side of the arrow has to be the same as the numbers on the right. So they have to add up to the same number. So let's take a quick look. We've got 92 on the left side of the arrow because we only have one reactant. And we've got 90 plus 2 on the right. 90 and 2. And that adds up to a total of 92. So our charge on both sides is balanced. We can take a look at the mass number and we see that we have 234 from thorium, 4 from helium to give us a total of 238. And then we also have 238 is our mass number on the right. So both our mass and our charge are balanced. Let's do some more examples. Here we have a series of 3 different reactions which all have a missing product indicated by the line. We're going to try to figure out what that product would be. So the way we do that is we use the same trick we just learned about, that the charge and the mass have to be balanced on both sides. So if the charge is 90, we'll start with the charge on the left. The charge on the left is 90. The charge on the right must also be 90. So we have to figure out what plus 2 equals 90. So if you want to figure out what plus 2 equals 90, hopefully you come up with the number 88. 88 plus 2 is equal to 90. We'll do the same thing for the mass number. We have 232 on the left, and we've got 4 on the right. So what plus 4 equals 232? If you came up with 228, that is correct. So then the question is, what is this element? So you have to go to your periodic table. You take a look at your periodic table, and you see what is element number 88, and you write down the symbol of that element. So if you determine that it was radium, that is correct. So the missing product was radium-228. We're also going to ask you to identify the type of decay. So this is an alpha particle, so we can identify it as alpha decay. In the next reaction, if we start out by looking at the charge, we've got 19 on the left and 18 on the right. So we're missing 1. 18 plus 1 equals 19. And you might have already noticed that the mass number is already balanced. So what do we put at the top for the mass number? If you thought 0, you thought correctly. So you need to go back now to table O and see if you can find which particle has that charge and mass number. If you determined a positron, you are correct. And we're going to add a little plus sign because that is a correct notation that's accepted for the positron, to differentiate it from a very similar looking notation for the beta particle. So right away, since we identified positron, we know that this is positron emission or decay. Now moving on to the last example. There's a little bit of a twist here because you'll notice there's the charge of 90 on the left and 91 on the right. So 91 plus a positive number could never give you 90. So this has to be a negative number. 91 plus negative 1 equals 90. And again, we have our mass numbers already balanced, so this would be 0. So looking at table O again, hopefully you identified that this is a beta particle. So right away we can identify as this reaction as being a beta decay. Symbolized like this. So we've got our beta decay, we've got our example of a positron emission, which looks like this, symbolized by this, and our alpha decay. So these are 3 balanced nuclear equations. Let's go on and look at a few more examples. So in these examples, we're asked to balance the equations where x represents our unknown that we have to figure out what it is. Now in the first example, x is on the left-hand side. So it's a little bit different from what we saw before, but we're going to apply the same techniques. So on the right side, we have the charge adding up to 7 plus negative 1, which is 6. So our x must have a charge of 6. And the mass number on the right adds up to 14, so it must also be 14 on the left. So which element, take a look in your periodic table, has an atomic number of 6? Hopefully you've identified it as carbon. So this is the answer for what x is. We've correctly identified x in this reaction. Feel free to pause the video and try the next 2 reactions and then watch for the solution. So in the second example, we've got 10 as our charge on the left and 9 plus x is charge on the right. So 9 plus 1 is 10. So we know the charge is 1. And in terms of the mass number, you should see that it has to be 0 because it's already balanced. So that should again look like a familiar particle from table O, and hopefully you've identified that as a positron. So this is our answer to number 2. Let's look at the final example. It's a little bit different because now we have 2 reactants and we haven't seen any nuclear equations like that before. So it makes the math a little bit trickier, but definitely manageable. So we've got a charge of 2 and 3 on the left, which adds up to 5. So we've got 5 on the left, and we have 1 here on the right. So 1 plus 4 has to add up to 5. So we know that our x has a charge of 4. Now if we look at the top, we've got 6 and 4 for our mass number, which gives us a total of 10 on the right. And we have 1 from hydrogen, So 1 plus 9 is 10. So we know our mass number is 9. So you have to go to the periodic table and look and find out what is element number 4. And you should find that it's beryllium. So that is the answer to the third and final example on this page. Let's move on now and see what we can learn from Table N. So here is Table N in front of you. It gives a list of selected radioisotopes. In case you're wondering, what is a radioisotope? A radioisotope is any isotope of any element that is unstable and will spontaneously decay. Now, it gives you in this table how it will decay in the decay mode. And all these symbols, in case you forgot what they are, can be found in Table O. So this one here, for example, if you look in Table O, is beta decay. This one here is alpha decay. And to help you, the nuclides here are listed alphabetically. So for example, you can be asked the type of question like this: what is the decay mode of cobalt-60? So you're going to go to Table 60 and go to C and find cobalt. And if you look in the decay mode column, you'll see that the decay is a beta emission or beta particles. So you would write beta decay, or you can symbolize it like that, beta decay. Either answer is acceptable. Now we have to write the nuclear equation for this decay. So the way to write a decay reaction where you know what one of the products are is to first write the reactant, and the reactant in our case is cobalt-60. So you write down cobalt-60 is the mass number. So you need to look up the charge or the atomic number of cobalt on the periodic table because most people don't have that memorized in their heads. So the atomic number is 27. So that is the charge of cobalt. And that is the reactant. Now we have to figure out what the product is, but we already have that information, or some of that information here. We know that the decay mode of cobalt-60 is beta decay, so one of the products must be a beta particle. So if you go to Table O, you can write in the beta particle symbol, which we usually write like this. So now we have enough information to figure out what the element produced will be, based on all the tricks we just learned about balancing nuclear equations. If we know that the charge on the left is 27, and we have a -1 on the right, what plus -1 equals 27? So hopefully you got 28. And then the mass number stays the same because of the 0 on the right. So 60 on the left, 60 on the right, and you go to your periodic table and you have to look up what is element number 28. And hopefully you got nickel as your answer. So that's how we write nuclear equations using Table N. It's a good time now to go and get the homework from Haiku and try it out. Thank you for listening and have a wonderful day.